Here's a ball being whirled in a horizontal circle, and we have the overhead view. It's a pretty massive ball, 1.5 kilograms. You can see the ball is green, and it's going around clockwise from counterclockwise from the overhead position here. And in part A, the counterclockwise doesn't really matter. We want to figure out or calculate the centripetal acceleration. It's simply v squared over r. So the centripetal acceleration, it tells us in this case the velocity, the tangential velocity as labeled in the diagram and stated in the problem is 3.3 meters per second squared. The units are good. Divided by the radius of the circle, we would like that in meters, so that's 0.75 meters. And when we calculate that, we end up with 14.5 meters per second squared. A sub c equals 14.5 meters per second squared. So that's our centripetal acceleration directed towards the center of the circle. Because there's a net force, a centripetal force towards the center, as labeled in the diagram. Now in part B, and by the way, there's a little diagram B here that just shows you the tendency for the ball to go in a straight line. If the string breaks, there's no longer a centripetal force, which is caused by the tension in the string. But assuming it's still attached in part B here, the centripetal force is provided by the tension in the string. So T equals mv squared over r, because T is the centripetal force, and centripetal force is mv squared over r. We could just take a shortcut right now and multiply our mass times the velocity, or times the acceleration we got in the first part, but I'll just plug everything in again just for illustrative purposes. The mass is 1.5 kilograms times the v squared, 3.3 squared, divided by that radius of 0.75 meters. So the tension, which is the only force, the net force towards the center in this case, the tension here comes out to be 21.8, you could just say 22 newtons towards the center of the circle. Then of course part C, calculate the centrifugal force, and the answer is you can't. That can't be calculated because it's a fictitious force. As we all know, the moon orbits the Earth. That takes just a little bit over 27 days, 27.3 days. The moon is held in orbit by a force of gravity. I'll direct that towards the Earth, F sub g. We also know that the moon is pulling back on the Earth with the same force according to Newton's third law, but I don't want to focus on that one right now. I'm just focusing on the force that keeps the moon in orbit in the circular path. F sub g is the centripetal force. I'm going to first calculate the centripetal acceleration, A sub c, which is v squared over r. We don't always have to do that, but it does ask us to do that in this problem, get the centripetal acceleration. But a side calculation I need to do, or I can incorporate it into this equation, but I'm going to just do it off to the side right now, is the velocity of the moon, the tangential velocity. The easiest way to do that, or I should say one way to do that, is to just use our equation v equals d over t, where d is one circumference, 2 pi r, is one circle, one path around in the 27 days. We have to watch our units here. So it's 2 times pi times the radius, which was 3.84 as given there, times 10 to the 8th meters, 239,000 miles, over the time. But I don't want to plug in days, I want to plug in seconds. And you can check this for yourself, but I did the calculation off to the side, and it turns out that 27.3 days is just over 2 million seconds. 2.36, so 2,360,000 seconds, so 2.36 times 10 to the 6th seconds. So the tangential velocity of the moon turns out to be just over 1,000 meters per second, 1,020 meters per second. Now that's over 2,000 miles per hour tangential velocity, but it's got a long way to go to get around the Earth in 27 days. Now I'm ready just to calculate the centripetal acceleration. That's 1,020 meters per second squared over that radius of orbit, 3.84, times 10 to the 8th meters. So the centripetal acceleration in this case comes out to be 2.7 times 10 to negative third, it's a negative third, meters per second squared. Same units as we always have for acceleration. It's amazing that it's moving with such high velocity, but the acceleration is very, very small, mainly because it's so far away. Now we need to figure out the centripetal force. If we want to call this part B of the problem, didn't really say A and B, so that was part A, let's call it part A. The centripetal force is mv squared over r, the mass times the acceleration. I'm not going to recalculate the acceleration again. The centripetal force is going to be the mass of the moon, given as 7.35 times 10 to the 22nd kilograms, times our acceleration, 2.7 times 10 to the negative third. The centripetal force, which is due to gravity in this case, is 1.99, could have just rounded it off to 2, times 10 to the 20th newtons. That's a huge force. That's the force of gravity, that's the centripetal force on the moon. Here's something you may have seen in a movie. A space station that simulates gravity. It's like a big wheel that spins. And you may have seen a similar type of thing in like a carnival, a small little rotating cylinder where you go inside and it spins fast enough and you stick to the wall. And you yourself will be saying, well, this is a centrifugal force, but really it's a centripetal force, something pushing inward on you, keeping you in that circular path. In this case, it's the floor of this station pushing in on this astronaut here or here towards the center of the rotation, or any astronaut that's right here or right here, pushing in as you go round and round and round. That can make it feel like there's gravity. It's a simulated gravity. Let's calculate the acceleration due to this particular rotation of this station, and that would just be calculated the normal way for centripetal acceleration, v squared over r. I'm going to do the calculation for v separately here. I'm going to do, well, distance over time again, like I did in the last problem with the moon. That would be 2 pi r over t. However, the adjustment in this case, I'm going to pick 60 seconds as my time frame, so that'll be 2 revolutions. 2 times 2 pi times the radius of this station, which is 225 meters, half the diameter, over 60 seconds. I could have gone around one rotation in 30 seconds. Will give me the same answer. It comes out to be about 47 meters per second, which is, I think, over 100 miles per hour, tangential velocity. But you're only making 2 revolutions per minute, like a revolution every 30 seconds. Anyway, the centripetal acceleration here will be 47 squared over the radius, 225, and this one happens to come out to be 9.8. That's perfect, because that actually simulates normal gravity. That's an acceleration not due to gravity, but it's simulated to make it feel like it's gravity, you know, like you're back on Earth inside the space station in outer space. Because one of the bad things in outer space is when you have apparent weightlessness, where you're floating around for days and days and weeks and months, your muscles and your bones break down and become weak, and it's not healthy. So if you simulate gravity like this, it can keep the astronauts healthier and make it easier to function as they do experiments and everything else in the space station. Here we have a car making a turn on a flat road at a constant velocity of 30 miles per hour, 13 meters per second. I have 2 views here, the overhead view on the bottom with the frictional force shown towards the center of the curve of the turn. The head-on view at the top there is probably a little bit more revealing. It shows you the force of gravity straight down, the normal force straight up. Those will be equal because the car's not accelerating up and down, but the force of friction is inward. It is the centripetal force in this case. So we've had tension in a string be the centripetal force. We've had gravity be a centripetal force. Centripetal force is a generic term In this case, the specific force that is the centripetal force is the force of friction. So the force of friction here, I'll call it F sub F, force of friction, is the centripetal force here. Now if you remember from the last few units, the force of friction can be calculated as mu times force normal. And the centripetal force in this unit is mv squared over r. Once again, if you're on a flat road, which we are in this case, the normal force, F sub n, as you should see in the diagram, is equal to the force of gravity, the weight of the car, which is mg. So that equals mv squared over r. Now, actually one thing to note on this, if I take r mu times Fn, that actually gives me the maximum, this is the maximum friction I can have. That's the maximum friction, because this is actually static friction. The only time you get kinetic friction with tires on a road with a car is if you go into a skid. This car is not skidding, it's maintaining its grip with the road. This is the maximum friction. And remember, static friction can be less than its maximum. But if we take the maximum friction here in this situation, which I've done, and set it equal to the centripetal force, this actually gives me the maximum velocity. So the condition for maximum friction matches the condition for the maximum velocity here. So as I go down here, I'll note that again as I start to simplify this equation. As you see now, I hope, the masses will cancel out on both sides because it's a part of single terms on both sides. You can divide it out of the equation. And if I move things around and solve for v, I'll do it in two steps. I'm going to multiply both sides by r. I'm going to have mu gr equals v squared. Then I'm going to flip things around and take the square root. You end up with v equals the square root of mu gr. That really is the maximum velocity of the car in this turn because we used the maximum friction equation up there at the top. So in other words, Vmax, the maximum velocity of this car, is the square root of mu, which is 0.6, times 9.8, times the radius of this curve, which is 50 meters. I need to take the square root of all that. And it turns out that Vmax here is 17 meters per second. 17 meters per second. All right, that's actually answering part B of this problem. Well, so that's part B. Part A says, will the car make the turn if he's going 13 meters per second? So the answer to part A is yes. Because the Vmax, you have to show and support it, what the calculation I just did, is 17 meters per second. On rainy days, the coefficient of friction lowers, like from 0.6 to 0.5 or 0.4, and that lowers your maximum velocity in a curve. Like you saw with the overhead ball example, example number, I believe, number 1 in these notes, if you exceed the maximum, in the example number 1, the string broke, the ball went in a straight line. Same thing here. If you exceed the maximum speed, friction doesn't break, but friction doesn't hold the car anymore, and the car would go in a straight line. I'll just illustrate that with a black mark here, because you don't want this to happen. You don't want to be going so fast your car ends up going this way into the ditch or into a tree off the road because you exceeded the maximum frictional force, because the car wants to go in a straight line according to Newton's first law.